In the deep reaches of the Pacific's warm tropical waters lies a realm of utter darkness, a world nearly frozen in silence. It is so perilous to explore that we know only the faintest details about what exists down there. For a long time, it was believed that finding any form of life down there was unthinkable. The conditions were so extreme that even the cells that make up living organisms would collapse. Bones and shells would simply disintegrate. The essential processes required for life would come to a complete standstill. That is, until 1960, when a living creature was discovered at the very bottom. It was the first undeniable sign of life in the abyss. But the story became even more extraordinary. Because down at these impossible depths, life didn't just exist, it was adapted to this realm in ways seen nowhere else on Earth. Much of what we know about this mysterious realm comes from long-distance sampling operations, or from the rare specimens occasionally brought up through deep-sea fishing. Extraordinary creatures adapted to conditions we still cannot fully comprehend sometimes drift ashore and wash up on our beaches. Once removed from the natural habitat, their forms begin to break down, many vanish entirely. Because of this, we can only speculate about what they truly look like and how they're able to survive in such extreme depths. The vast and boundless expanse of the deep ocean floor represents the last great untouched frontier still awaiting discovery on our planet. In this chapter, we embark on an unforgettable journey toward the most extreme point of our oceans, the Mariana Trench. Our journey takes us back nearly 150 years, to the closing days of the HMS Challenger's 4-year mission, the first expedition to produce detailed maps of the ocean floor. The crew had carried out hundreds of depth measurements, enduring every kind of weather, from scorching tropical heat to the icy waters of the polar seas. They lowered the lead weight until it touched the ocean floor, and then hauled the cold, heavy, water-soaked rope back up for meters and meters. What emerged was a landscape 3 to 4 kilometers below the surface, a muddy, silt-covered seafloor, almost completely flat and utterly featureless. East of the Philippines, in the middle of the vast open ocean, during one of their routine measurements, with not a single piece of land anywhere around them. But this time, the lead weight did not reach the bottom at 3 kilometers. It didn't stop at 4 kilometers either, not even at 5. The weight continued descending into the dark, empty abyss. Eventually, the lead weight reached the seafloor at a depth of more than 8 kilometers. The place they had discovered is what we now know as the Mariana Trench. Had they gone just a little farther west, they would have found the deepest point on the planet's surface, Challenger Deep. An 11-kilometer abyss. If you were to place Mount Everest, the highest peak on Earth, inside this trench, its summit would still lie 2 kilometers below the surface. The Mariana Trench is a structure whose scale defies comprehension. Imagine a curved valley stretching along the ocean floor for roughly 2,500 kilometers, nearly 70 kilometers wide. It begins about 2,000 kilometers south of Japan, curves southeast, and then bends westward as it extends toward the Philippines. On the western side of the trench rise steep, towering walls formed by exposed masses of magmatic rock. To the east, the terrain lifts more gently, opening into an almost completely flat and featureless oceanic plateau. This vast plain stretches uninterrupted for nearly 12,000 kilometers, reaching all the way to the coast of Mexico. Visualizing a structure of this scale is extraordinarily difficult. This abyss is so deep that even if you stacked 33 Eiffel Towers on top of one another, the top of the last tower still wouldn't reach the shore. The Mariana Trench is one link in an unstable, ever-shifting chain of deep ocean trenches that almost completely encircles the Pacific Ocean. These deep trenches also coincide with the volcanic belt we know as the Ring of Fire. Along this 40,000-kilometer fracture line in the Earth's crust, intense geological motion is responsible for nearly 90% of all earthquakes on the planet. Throughout these regions, immense blocks of rock, stretching down for kilometers, grind, compress, fracture, and in some places disappear entirely. We are only now beginning to understand how the surface of our planet has changed over time, how the continents arrived at the present positions, and why these deep fractures play such a vital role in this grand story. To understand this extraordinary geological structure, it is best to begin by looking across the Americas, toward the Atlantic Ocean. The surface of our planet is made up roughly of continents and oceans. But this isn't simply a distinction between land above the water and ground beneath the sea. Continents and ocean floors are two entirely different components of Earth's crust, and all of them float atop a layer of hot, semi-molten rock we call magma. Continents are like giant icebergs floating on top of the magma. Most of their mass, just like icebergs, remains hidden deep below. The spaces between the continents are filled by the oceanic crust, a remarkably thin shell, no thicker than the skin of an apple when scaled to the size of our planet. Continents are incredibly ancient. They are formed from thick masses built up over billions of years as countless layers of rock accumulated on top of one another. The oceanic crust is far younger, only a few million years old. It is thinner and made up of solidified products of molten magma. Both the ocean floors and the continents are slowly carried along by vast convection currents created by the heating and cooling cycles of the molten mantle beneath them. There was a time when all the continents on Earth were joined together as one immense landmass, Pangaea. For nearly 200 million years, this vast process has unfolded. Pangaea began to break apart, its colossal plates slowly drifting away from one another. The oceans widened, and the continents gradually migrated into the positions we recognize today. The Atlantic Ocean expands by a few millimeters each year, slowly pushing the Americas away from Africa and Europe. As the camera glides toward Earth from a west to east global view, the widening ocean becomes clearly visible between the drifting continents. As the continents drift apart, the gap between them is filled by newly formed oceanic crust, a continuous creation of seafloor. At the very heart of the Atlantic lies a gigantic fracture line, the Mid-Atlantic Ridge. What drives the widening of the ocean floor is the thermal magma rising from deep within the Earth. As it ascends, the molten rock spreads outward, eastward and westward, pushing the continents apart and inserting new layers of crust between them. When magma reaches the surface, it cools, solidifies, and becomes new oceanic crust. This process never stops. As the Atlantic continues to grow, its freshly formed crust appears in dark, young basaltic tones. The Americas can be seen drifting slowly westward, moving away from Africa and Europe. As a natural consequence of this motion, the continents gradually move closer to Asia and Australia over time. As the continents continue moving westward, the Pacific Ocean gradually narrows. The same magmatic forces that widen the Atlantic are also at work beneath the Pacific. Beneath the Pacific Ocean, powerful magma currents constantly generate new oceanic crust, forming what we know as the Pacific tectonic plate. Like an enormous geological conveyor belt, it drifts outward in a slow, steady flow. The Pacific plate moves slowly across its vast surface, like a colossal conveyor belt pressing steadily toward the surrounding continental margins. If the Pacific is shrinking, then where does all the newly formed oceanic crust go? The answer to this question lies hidden within the Mariana Trench. When the Pacific plate meets the surrounding continents, it has nowhere left to go, and is forced to dive beneath them. This mechanism is the planet's largest recycling system. It is the force that creates earthquakes, chains of volcanoes, and the vast ring of fire encircling the Pacific. When oceanic crust sinks into the mantle and melts, part of that material rises again and erupts at the surface as volcanic activity. This is why subduction zones feature deep ocean trenches and chains of volcanoes on the landward side. As the Pacific plate moves toward the Mariana Trench, it cools, becomes denser, and is pulled downward by gravity. This causes the ocean in that region to grow steadily deeper. At roughly 170 million years old, this plate is the oldest oceanic crust on the planet, and it is now nearing the end of its geological life cycle. In the western Pacific, this ancient plate collides with the younger and lighter Philippine plate. The Philippine plate remains on top, forcing the Pacific plate downward and bending several kilometers of solid rock with it. This immense collision boundary is the very place where the Mariana Trench was formed. This zone of destruction hosts some of the most extraordinary features on the planet: massive mud volcanoes, up to 50 kilometers wide, that release hydrogen into the Pacific waters, carbon dioxide vents where the gas rises in liquid form under extreme deep-sea pressure, and crater pools filled with molten sulfur, a phenomenon observed only here and on one of Jupiter's moons. From the deep fissures in this region, mineral-rich superheated water rises, and some scientists believe that these hydrothermal vents may hold clues to the origins of life on Earth. At 10,935 meters, the Mariana Trench may seem like a geological anomaly, an unusually deep scar on the ocean floor. But in reality, other trenches around the Pacific reach similar depths. The nearby Tonga Trench descends to 10,800 meters, and the Philippine Trench drops to 10,540 meters. These immense trenches are constantly shifting, and the depression that forms Challenger Deep is only a temporary shape within Earth's dynamic structure. One day, this depth will disappear, and the title of the deepest point on Earth will pass to another place entirely. The greatest challenge in deep-sea exploration is pressure. Even a few meters in a swimming pool can strain our ears. In places like the Mariana Trench, the pressure rises to more than 1,000 times that at the surface. Such force can crush ordinary living cells, and even highly engineered machines. In 2014, the unmanned submersible Nereus was lost when it suddenly imploded under extreme pressure in the Kermadec Trench. Even modern military submarines can safely reach only about 1,500 meters. To reach the bottom of the Mariana Trench, far stronger, purpose-built vessels are required. In 1960, Don Walsh and Jacques Piccard achieved the unthinkable. They descended into the Mariana Trench aboard a small bathyscaphe named Trieste, a vessel with a buoyancy tank above and a thick, spherical pressure capsule below. At around 9 kilometers, a deafening crack echoed through the cabin. Unaware that one of the outer plexiglass windows had fractured, they continued downward, pushing Trieste to its technical limits. It took nearly 5 hours to reach the bottom. Their view was limited to a narrow beam of light through two tiny 5-centimeter windows. When Trieste touched the seafloor, a cloud of sediment erased all visibility. They remained at the bottom for only 20 minutes before beginning the long ascent, which took more than 3 hours. The mission was so risky that nearly 50 years passed before another human reached comparable depths. During that time, around 7,000 people climbed Everest, and 12 walked on the moon, highlighting just how immense the technical challenges of exploring the deep ocean truly are. The next manned descent occurred in 2012, when James Cameron completed the first solo dive to Challenger Deep aboard the Deep-Sea Challenger. Over the years, more than 20 missions followed, and the number of people who have reached Challenger Deep eventually surpassed the number of astronauts who have walked on the moon. In 2021, Hamish Harding completed the longest and deepest manned dive to Challenger Deep, setting a new milestone in deep ocean exploration. Tragically, just 2 years later, Harding became one of the 5 people who lost their lives when the Titan submersible imploded at a depth of 3,800 meters. This tragedy once again underscored the immense risks involved in deep-sea exploration. When we return to the surface, all that surrounds us is a limitless, featureless expanse of water. No matter which direction we look, the nearest land lies more than 300 kilometers away. This vast emptiness conveys the true scale and the profound isolation of the open ocean. The tropical sun floods the upper layers with radiant light. Beams of sunlight pierce the water, carrying the energy that sustains all life in the ocean. The scene is both visually breathtaking and scientifically essential, a glowing world shaped entirely by light. We are now in the epipelagic zone, the euphotic zone. Although it makes up only 2 to 3% of the ocean's volume, this thin upper layer is where all life begins, feeding ecosystems both at the surface and far below. In this bright upper layer, phytoplankton, including diatoms and photosynthetic bacteria, produce nearly half of the oxygen we inhale. This single fact reveals how crucial it is to protect our oceans. Larger fish hunt the smaller ones, and sharks prey on the larger fish. The entire food chain is powered by the energy first captured in this narrow sunlit layer. Afterward, we enter the twilight zone, the mesopelagic or dysphotic zone. In this layer, a small amount of light still penetrates, but not enough to support photosynthesis. Temperatures are far lower than at the surface, and as the darkness deepens, the first glimmers of bioluminescence appear from creatures capable of producing their own light. This part of the ocean is extraordinarily rich in life. In fact, the total biomass of fish here may equal, or even surpass, that of all the fish in the rest of the ocean combined. Yet as we continue descending, you'll notice I begin using phrases like, probably, most likely, or, as far as we know. That is because our understanding of the oceans, and the creatures that inhabit them, remains extremely limited. Here, at the meeting point of light and darkness, lives the most abundant vertebrate species on the planet, the bristlemouth. This small, 7 to 8 centimeter fish with needle-like teeth may not look impressive, but its population is almost unimaginable, likely in the quadrillions. Their intense feeding on zooplankton is one of the clearest indicators of just how powerful the sunlit surface layer is as the engine of life for the entire ocean. We are now about 1 kilometer below the surface, in the bathypelagic zone, the region one called the midnight zone. This layer represents the largest living space on Earth, covering more than half of the planet's surface area. And yet, our understanding of what truly happens here remains surprisingly limited. Down here, the temperature remains fixed at around 4 degrees Celsius. The environment is cold, stable, and eerily quiet, a stark contrast to the world above. The crushing weight of the water above has now reached lethal levels. We are far beyond the practical limits of human diving. Even pressurized diving suits cannot reach a depth like this. At this point, we have long surpassed the maximum safe range of even nuclear submarines. As a species adapted to surface conditions, we often imagine these depths as a kind of uninhabitable hell. But for the creatures that live here, this environment is completely natural. They are perfectly adapted to the cold, the darkness, and the crushing pressure. When our cameras illuminate the water, they reveal what looks almost like an underwater snowstorm, countless microscopic organisms and drifting organic particles known as marine snow. And especially in the upper parts of this zone, there is far more movement and life than we might expect. As we move deeper, creatures with increasingly strange appearances begin to emerge. Some have disproportionately large eyes, allowing them to detect even the faintest traces of light in what appears to us as total darkness. It is difficult to imagine exactly what they see, but for them, it is more than enough. The owlfish uses even the slightest glimmer to hunt shrimp and jellyfish. The barrelea, with its upward-facing tubular eyes, tracks its prey from below and is believed to survive in near total darkness at depths reaching 2,500 meters. Some species, however, have taken the opposite path and have almost completely abandoned vision. The small-eye snipe eel is a perfect example. Down here, having large eyes serves no purpose. If you are not using light to hunt or communicate, eyesight becomes nothing but wasted energy. The giant squid, the creature with the largest eyes on the planet, has become an almost mythical inhabitant of this dark world. Only a few have ever been filmed, the longest recorded specimen measured around 13 meters. But nothing in science rules out the existence of even larger ones. Perhaps, far beyond our reach, truly enormous giants drift silently through the darkness. As we descend deeper, the drifting particles we once saw in the upper layers disappear entirely. Every organic fragment that falls from above has already been consumed by something along the way. Less than 1% of the organic matter released at the surface is able to reach these dark depths. So down here, this is not a feeding ground for scavengers in the traditional sense, it is a brutal hunting arena. You are either predator or prey. The chimera, also known as the ghost shark, has lifeless, pale eyes, wing-like fins that allow it to glide through the water, and, like many creatures that inhabit these depths, a disproportionately large head. Unlike other sharks, it carries a set of permanent teeth that last a lifetime, strong enough to crush even the hardest-shelled animals it encounters. It is equipped to consume almost any creature it crosses paths with, large or small. The pelican eel is one of the strangest creatures in the deep ocean. It possesses an enormous mouth and an elastic stomach that allows it to swallow prey even larger than itself. This unusual ability also serves as a defensive strategy, making it harder for larger predators to capture or consume it. As we pass beyond the lower boundary of the midnight zone, we reach the deepest layer of the ocean, the Hadal zone. Its name comes from Hades, the ancient Greek god of the underworld. So far, only about 400 species have been identified here. 400 may not sound insignificant, but when a simple freshwater lake can hold thousands of species, this number is ecologically almost nothing. Here, we encounter some of the deepest dwelling fish known to science, including the Mariana snailfish and the cusk eel. Yet it is entirely possible that many more species live here, we simply haven't met them yet. Clinging to the rocks are strange, gelatinous masses. These are xenophyophores, single-celled organisms that can grow up to 20 centimeters, nearly the size of a football. For a single cell, such size seems almost impossible, yet in an environment that would be lethal to surface-dwelling cells, they thrive. As we sink into the deepest waters, even the Mariana snailfish and cusk eel vanish from sight. And this leads to the real question, what about the things we cannot see? Why do we still know so little about a region that covers more than half of our planet? What secrets are hidden in the darkest depths of the ocean? I like to imagine a future in which scientists, driven by curiosity, finally gain the tools needed to explore these extraordinary depths. And when that day comes, I hope we will share with you the remarkable discoveries and scientific breakthroughs they uncover as they illuminate this mysterious world. I put a great deal of effort into bringing this journey to you. If you enjoyed it, I would truly appreciate it if you could like the video, follow the channel, and share your thoughts in the comments.